So we're starting the second video with a correction that I had to make. So first of all, I apologize, but if you go to D2L, I have a correction for this part of the solution. Alright, so I uploaded an image that has these corrections. So what I'll do is I'll go through the rest of this problem, show you what I missed. Basically, I just missed a variable, which changed the value of my solution at the very end of this problem. So we left off with an expression for the tension, right? The tension in the cord that's wrapped around the wheel. Excuse me. So what the plan is to take this expression for tension and then substitute it up here for T. Okay. So we have Newton's second law for the bucket. The bucket is traveling in the y direction. I use Newton's second law for the wheel, Newton's second law for rotational motion, to derive an expression for the tension, because the question is asking us find the tension in the cord and then the acceleration of the bucket. So I missed an m sub b here. Okay, so I went in and I substituted an m sub b. Okay, so this is Newton's second law for the bucket. I took this expression for T, right? 1/2 the mass of the disk times A, and I substituted that in. So now I have an expression for A, and all I have to do is do some algebra, solve that expression for A. So this term has an A in it, this term has an A in it. I'm going to add this term to both sides and get all the terms with A in them on one side of the equation. Alright, so I've got the mass of the bucket times A plus 1/2 the mass of the disk times A is equal to the mass of the bucket times the acceleration due to gravity. So I have the masses for the bucket and the disk. I know the acceleration due to gravity. Now it's just algebra time solving for A. Both of these terms have A in them, so I can factor them out. So in this term I have the mass of the bucket plus 1/2 the mass of the disk. So now I'm going to divide both sides by this term, get A by itself, and so here's my expression for the acceleration. And you see where I missed that mass of the bucket term. I had a 1 there first, right? So now instead of just having a 1, I have the mass of the bucket there, which is 2 kilograms. So I substitute all my values. Both the mass of the bucket and the mass of the disk are 2 kilograms. So a good thing to do in preparation for the exam is you'll probably see something similar to this in a WebAssign problem, right? So for practice, and they randomly generate values for you. So set up a problem like this and make up your own masses, right? Give the bucket a larger mass, give the wheel a larger mass, something like that. Give it nice numbers, and then just go through the problem from the beginning. That'd be really good practice. So I substitute my values in for the acceleration, and I get an acceleration of 6.5 meters per second squared. So now I have the acceleration. I can substitute that in here and solve for the tension. And when I solve for the tension here, I get a tension of 6.5 newtons. Okay. So again, the process is the same. I apologize again for my typo. It was, you know, typos have pretty significant consequences in these problems. But Newton's second law for the bucket, free body diagram for the bucket, like we did back in chapter 4, and then Newton's second law for the wheel. But we have a new Newton's second law for rotational motion. All right. And another important thing to take away from this is that the moment of inertia is not just the mass anymore, so we have to look up the moment of inertia for whatever object is rotating, and then we have to substitute our relationship between our angular acceleration and our tangential acceleration in for alpha, because what we're looking for is a system of equations, right? Two equations, two variables, in terms of tension and in terms of the linear acceleration. This will be the case for any object that's rotating. The tangential acceleration of any point on the edge of that object, the tangential acceleration of any point on the end of that object is going to be equal to the linear or the translational acceleration of some object that's moving and is connected. Okay, so this bucket has an A, the wheel has an alpha, but this alpha is this A divided by R. So that's a very helpful relationship to be used later. Okay, so the bucket applied a force on the wheel, or we'll say the tension in the cable directly applied a force to that wheel. So that tension was causing the wheel to rotate. The wheel was initially at rest. It had some angular velocity some time later. So we were accelerating it. It rotated. So there was a point on the edge of that wheel that was moving. Okay, so we were displacing the wheel rotationally due to a force. So that's the definition of work, right? You're moving some object due to some force, you're doing work. So we have to be imparting some energy onto that wheel, right? If you rotate an object, you apply a force, you're displacing that object rotationally, you're accelerating it. So you have to be doing work, you have to be imparting energy onto that object. So that means if an object is rotating, it's got to have some unique form of kinetic energy. So what we're going to do, since we're dealing with solid objects, I want to picture, this is just a general object, right? It doesn't have any, nice shape to it. But we can split it up into a bunch of little tiny blocks, right? Let's just say we take we take something and we cut it up into little tiny cubes, say, right? Little tiny objects. So those are little tiny point particles, right, that are resting inside the solid object. Now when you do work, you move all of those particles, right? You rotate all of those particles. Okay, so we've got a bunch of M's, a bunch of little M's, okay, inside this object. And each one of those little masses, each one of those little objects, they have a tangential velocity, right? They have a tangential velocity because they're rotating, but they have their own unique tangential velocity because they're a different distance, they're a different R from the axis of rotation, right? So the farther away you are from the axis of rotation, the greater your tangential velocity is going to be. So here's what I did, sparing us the rigorous calculus. So what I did was I took all of these little M's, right, all of these little tiny masses that are inside my object, and I said every single one of them has a kinetic energy, right? They've got a mass, they've got a tangential velocity, so they all have to have a 1/2 mv squared. So I'm using summation notation. Okay, so let's say I have I little pieces of masses inside my object. So I said the sum from I to, well, in this case maybe infinity or whatever, it won't necessarily be a sum that we have to evaluate. Alright, so let's say we have I little masses with their own unique tangential velocity. Okay, so they're different distances from the axis of rotation, so they have their own tangential velocity. So every single one of these little pieces of the object have a 1/2 mv squared. So the tangential velocity of all of these objects here, since they're rotating, they also have an angular velocity. So this is my relationship between the angular velocity and the tangential velocity. So I'm substituting omega I Ri in for v sub I. Alright. So I've got this expression in for the tangential velocity of each object. Now each little tiny particle is a different distance away, right? So Ri is going to be different, and Mi is still going to be different, right? These two properties are unique amongst all of these little particles, but the whole object is rotating at a constant angular velocity. So that's the one thing all of these objects share, right? The mass is different, the distance from the axis of rotation is different, but omega, the angular speed, is the same for all of these particles. So I can factor out that omega because it's constant, right? The 1/2 and the omega I can factor out of this sum because it's constant. It doesn't change, okay? And so now I have this. Now I have this expression. So it's the sum of all the mr squareds of each individual object. Now, I've been talking about solid objects, you know, steel beams and disks and spheres and all that stuff. If I had a point particle, right, if I had a mass on the end of a string and it was spinning around in a circle, it would have a rotational inertia mr squared. So this expression right here is actually the moment of inertia for a point particle, right? Not for a solid object. This is for a point particle, okay? And we'll use that later, right? Because what we'll have is we'll have a solid object rotating, and then like a point particle will land on it, okay? And it will change the moment of inertia of the object. So we'll use this mr squared when we're dealing with a point particle. But we've got I point particles, so we're summing over all those point particles, right? And if this is a rigid object, right, this is a solid object, a sphere or a disk, this is the expression for the moment of inertia for that entire object. So this right here, again, barring the calculus for the solid objects, this would turn into an integral for like a sphere or something like that. We already have these formulas. So this is an expression for the moment of inertia for the entire object. So now we have a kinetic energy, 1/2 I omega squared. So any object that's rotating, this is the expression for the rotational kinetic energy of the object. Now this whole thing isn't moving in the x direction or y direction right now, so it doesn't have a linear kinetic energy, it just has a rotational kinetic energy. So when you grab a wheel, like your steering wheel or something, and you turn it, you're doing work, you're accelerating it, and you're imparting some energy to it. And so you're increasing its kinetic energy. Okay. So these units are kilogram meters squared, right? Those are my units for moment of inertia. Okay. So I have kilogram meters squared here, and then I have radians per second squared here. So these are units of energy. Kilogram meter squared per second squared. Okay. So these are units of energy. All right. So again, the moment of inertia depends on the axis of rotation. We're going to do a lot of problems where we can pick a convenient axis of rotation. All right. So again, all these little pieces have their own little MVs, M's and V's, M's and V's, but they have the same angular velocity. Right? So we use that property to derive this new expression. Okay. So this is we still see a lot of similarities, right? We're seeing the rotational analog of what we did in chapters 4 and 5, right? The concepts of force and energy are being applied to an object that's rotating now. So let's take this object, let's say it's a sphere, right? Let's say it's a sphere or a disk, right? Some ball rolling across a surface. So this object, right, it's rolling, and we call this rolling without slipping. All right, so that means this object isn't like skidding across the surface, right? It's not slipping. So there's friction in between this object and the surface, right? There has to be friction, otherwise it would just keep spinning, like your tires are spinning on the asphalt. So it's rolling, it's not slipping. There's static friction. Okay, there's static friction between this object and the surface. But static friction doesn't do work because static friction doesn't cause an object to displace. All right, so this static friction is applying a force on this object, but it's not doing work. All right, so we can use energy concepts for this type of situation. So again, when we were talking about like rotational kinematics, right? And so we said the total distance, right? If you look at this arc here, right? This is the total linear displacement of this sphere or disk, whatever it is. So from here to here, that's the delta x. But you see that it travels an entire circumference. Right? And it travels an entire circumference from this point to this point. Okay. Picture like a ball of string or something. If you roll it and the string stays on the floor, right? This delta x is one circumference. Okay. But this velocity, right? This whole thing has a linear velocity, and that's the velocity of the center of mass of the object. Again, in this course, all the objects will have a uniform mass distribution. So every point on this object has the same velocity, right? So this is the tangent or the linear velocity from last time, or from kinematics. So this object is doing two things, right? It's rolling, so it's rotating, and it's also traveling linearly. But we see we have the same relationship, right? The tangential velocity, what used to be the tangential or the linear velocity, it's also the same as the velocity of the object's center of mass. And so we still have the same relationship as we did in rotational kinematics, okay? That the velocity, the linear velocity of this object's center of mass is equal to its angular velocity times the radius of the object. So this relationship still holds. Okay. So this object has two forms of kinetic energy. It has linear kinetic energy, right? The linear velocity of the center of mass. Okay. The linear velocity of the center of mass. But it's also rotating, so it also has an angular velocity. So if you have a ball or a disk rolling, it's got 1/2 mv squared. It's got a linear kinetic energy. It's got a translational kinetic energy, and it's got a rotational kinetic energy, right? So before, when we were just rotating an object like this, it was stationary about its axis, or its axis was stationary. It only had rotational kinetic energy. So we're going to deal with an object that is rolling. So it's got a translational kinetic energy and a rotational kinetic energy. Okay, so something to think about when we have objects that are behaving this way. And I'll do a couple examples, because before we used to have like a block sliding down an incline. We didn't have to worry about it rotating. If you take an object that can roll down a hill, we have to account for the two different types of energy it has as it goes down the incline. Right? So this is our new kinetic energy term for an object that's slipping. So let's start with a basic example here. We're going to take a sphere. Again, watch for the shape of the object. Okay, so I could go back and forth. What's going to be able to roll down an incline, a sphere or a disk? So make sure you can identify the type of object. So we get the mass of the object. It's a sphere. It's got a radius of 1/2 meter, starting at rest at the top of a 15-meter tall hill. So we have the height of the incline. We've got the mass of the sphere and the radius of the sphere. We want the velocity, and it says linear velocity. So I'm being a little specific here, right? I want v. Okay, I don't want omega. I want v. But what you could do for practice is just a little step at the end. You can find the angular velocity as well. So we're looking for the linear velocity, v, of the sphere at the bottom of the hill. So here's my picture, right? The incline is a height h. My sphere is at the top. I let go of it. I release it from rest, and then it goes down the incline and then reaches the bottom. Now the bottom, again, I'm still in amber. It's been a while, but I'm still in amber. This kind of got cut off here. This is my zero potential configuration, right? So I'm going to say the potential energy of this sphere is 0 at the very bottom of the incline. So I look up the moment of inertia for the solid sphere. Okay, it's 2/5 mr squared. All right, so I'm going to use that as the moment of inertia for the sphere. again, the only friction that is occurring here is rolling friction. If this was totally frictionless, it would just slide down and wouldn't rotate. But this is rolling friction, so it's static friction, it's not doing any work. So I can use law of conservation of energy to solve this problem. So I'm going to say that the initial gravitational potential is equal to the final kinetic energy of the object. But at the end, at the bottom of this incline, it's going to have linear kinetic energy, translational kinetic energy, and it's going to have rotational kinetic energy. Right? So I've got two kinetic energy terms over here. Right? Set them equal to the initial gravitational potential energy. Starts from rest, so there's no initial kinetic energy, so I don't have to worry about that term. Now I'm ready to substitute, right? Because what am I looking for? I'm looking for v. I'm looking for the linear velocity. But I have a problem over here with my rotational kinetic energy term, right? It's got I, which is okay. All right, I've got the mass and the radius, right? I can calculate that. But it's got omega. So I'm going to substitute, and again, I'm going to wait till the very end to substitute my values because I want to see variables that cancel to make my calculation easier. So I'm substituting 2/5 mr squared in for the rotational inertia of the sphere, but I'm substituting this v over r, because that relation still holds for a solid object. V over r I'm going to substitute in for the angular velocity. Okay. Now right here, don't forget v is being squared and r is being squared. This is a fraction, right? So I'm going to distribute that exponent to the numerator and the denominator. So what goes away? The 2's go away. Every term has a mass. That's great. Right? Here's the mass, here's the mass, here's the mass. Every term has a mass, so I can divide both sides of the equation by the mass. They go away. Square the v, square the r, and the radius goes away here. Right? The r squared terms go away. So that's good. So I've got 1/5 v squared plus 1/2 v squared is gh. So I'm solving for v. Let's factor a v squared out. I've got 1/5 plus 1/2. Find the common denominator, whatever you want to do. I got this little trick that I like to do. 1/5 plus 1/2 is equal to the product of these two, right? 1 times 2, plus the product of these two, 1 times 5, divided by the product of the denominators, 10, right? And I get 7/10. So that's just a little cheat that I like to do. I don't like trying to find common denominators. It always annoyed me, so somebody taught me this trick, and so I've just used that from now on. So I divide both sides by this, 1/5 plus 1/2, and I get 7/10 there. And dividing by 7/10 is the same as multiplying by 10/7. So now I've got a nice expression for v squared. Take the square root of both sides. V squared is root 10/7 gh. Now, when I was dealing with energy for an object that wasn't rotating, this used to be a 2. So if you notice, this is less than 2. Right? So what does that mean? That means the initial gravitational potential has to be split between these two types of energies now. Right? So it's not all linear kinetic energy. Right? That's why this number is less than 2, what it used to be. Some of that gravitational potential is transformed into the rotational kinetic energy. So I've got an expression. This is for a sphere, right? If we did a disk, this would be a little bit different, right? It would still be less than 2. So I've got root 10/7 gh. I have the height of the incline. I've got the acceleration due to gravity. And I can plug those in and get a final velocity. What if I was asking for the angular velocity? I can do two things. I can take this, substitute it in here, divide it by r, find the angular velocity. Or I can start at the very beginning, and instead of substituting v over r for omega, I can substitute omega times r for v right here. And I go through this whole process. So give this a try. Take this step, get to this step, and it says instead of substituting v over r in for omega, substitute omega times r here for v, and then go through the same thing but solve for omega, and then see how this changes. Alright, so go through that process. That'd be nice practice. So you'd get an expression for the angular velocity, and then you can still find both velocities, right? Angular and linear. using that relationship. Alright, so here's a big one. Here's a big problem. I've got an Atwood machine. What's the Atwood machine? We've covered the Atwood machine before. Okay, we've got a pulley with two masses on either side, right? And so we use Newton's second law. We found the acceleration of the system. We had like two equations, two variables, right? And we solved for the tension, solved for the acceleration. Now previously, we assumed the pulley was massless. So what that means is that there is no necessary energy that has to be imparted to rotate this. Okay? And the two tensions were always the same. In this scenario, I've got two different tensions on either side of the pulley. Now why? Why is that true? Why aren't the tensions the same anymore? Because let's say M1 was the larger one, right? Let's say M1 was larger than M2. You can draw it however you want, right? You can put the larger mass on this side, larger mass on this side, no big deal. Let's say M1 was the larger mass. So I predict M1 is going to descend, M2 is going to ascend if I let go of the system. So I let go of the system, what else happens? This pulley starts to rotate. It was initially at rest. So it has to have some angular acceleration. In order to have some angular acceleration, there has to be some net torque applied to it. If there's a net torque, there's a net force applied on this. So if T1 was equal to T2, the net force would be 0, and we wouldn't have an angular acceleration. So these tensions have to be different for a net torque to be applied on this pulley. So that's why now the tensions on either side of this pulley are not equal to each other. So I'm going to give them two different terms, T1 and T2. So here's my diagram of the modified Atwood machine. So I know the two hanging masses, 7 kilograms and 5 kilograms. The pulley is a solid cylinder, so it's going to have, I've used the cylinder quite a few times, right? Again, you have the moment of inertia available. You don't have to memorize them, but we'll use them often enough that we'll just kind of accidentally start memorizing them, right? So the cylinder is 1/2 mr squared. I've got the mass of it, I've got the radius of it. It's in centimeters. Don't forget we got to convert it to meters. We're looking for the acceleration of the system, all right? So if somebody says velocity or acceleration and they don't say angular, we're going to assume they're talking about the translational velocity. Right? If they don't say the word angular, we're going to assume translational or linear. Okay? Because once we find the linear acceleration, linear velocity, we can just divide both of those terms by r and get the angular components. So we're looking for the acceleration of the system and the tension of both strings. Right? So I'm looking for A and I'm looking for T1 and T2. So basically this is the well problem, right? The bucket and the well problem, except we have two buckets on either side, right? So I'm still going to start with a free body diagram for M1. Again, I'm going to define my coordinate system that's convenient for me, which is opposite the convention in this case. So I put M1 on this side, it's the larger mass. I'm going to predict that it's going to accelerate in this direction. So the acceleration for M1 is positive when it's down. The acceleration for M2 is positive when it's up. And so the rotation of the pulley is going to be clockwise, so I'm going to say clockwise is positive. So clockwise is positive for the pulley, down is positive for M1, up is positive for M2. So we're going to go around like this. Alright, that's the direction of my acceleration. Up this way, around, and down. So my free body diagram for M1 is T1 in the positive y, M1g in the negative y. Same thing for M2. T2 in the positive y, M2g in the negative y. So this is my free body diagram for the pulley. Technically there's a gravitational force on the pulley. That is true. But it's being fixed, right? It's it's held up by some structure that's keeping it stationary, right? So there's a contact force here at the axis of rotation. It's technically a normal force, it's a contact force. So there's a normal force in the positive y, gravitational force in the negative y. They cancel each other out because there's no acceleration. It's stationary, okay? But just to be thorough, we've got those two forces. And then we've got T1 causing it to rotate this way, and then T2 causing it to rotate this way. So these are the two forces that I'm concerned with that are going to rotate the pulley, T1 and T2. Alright, so I'm going to write Newton's second law out for all three of these objects. M1 is accelerating, so M1G is positive to match this direction, my convention. T1 is negative, it's equal to M1A. So here's my Newton's second law. For M2, same thing, except T2 is positive to follow the direction of the acceleration. T2 is positive, M2G is negative. That's equal to M2A. Newton's second law for the pulley is the sum of the torques on this object is equal to its moment of inertia times its angular acceleration. Alright, so for an object that's rotating, my Newton's second law is tau equals I alpha. So what are the torques being applied on the pulley? So there's a torque due to T1. It's being applied a distance r from the axis of rotation, which is the radius. Okay, so T1 times r, the radius vector and the T1 vector are perpendicular. So sine of 90 is 1. I don't have to worry about my sine theta term. Same thing for T2. T2 is applying a torque. It's applying a force at distance r. So the torque being applied on the pulley by T2 is T2r. Okay, again, for the same reason, the vectors are perpendicular to one another. I don't have to worry about the sine theta term. But again, T2 is causing a counterclockwise rotation, which I define to be negative. T1 is applying a clockwise rotation, which I determine to be, or I define to be positive, right? So plus T1r minus T2r is the moment of inertia of the disk, 1/2 md, so I'm using m sub d for the disk, r squared. That's an alpha right there, sorry. My bad picture taking skills. That's an alpha, that's the angular acceleration. So I need to find T1, T2, and A. So that's three variables, unfortunate, but I do have three equations. I think that it's possible, well, it should be possible, to use the linear combination method to solve for this system, but I think that's going to be messy and complicated, so what I'm going to do is I'm going to do the substitution method. So I'm going to take this expression, solve it for T1, this expression, solve it for T2, and then I'm going to substitute both of them in for this. So I'm going to get rid of the T1 and T2, and I'm going to only have A left. Now remember, just like with the bucket, any object that's rotating, this angular acceleration is related to this linear acceleration by this relationship. Alpha is A over R. So anytime I see an angular acceleration and I'm asked for A, I'm going to substitute A over R in for alpha. So here we go. I'll do algebra, solve this for T1, solve this for T2. I've got expressions, right? They're in terms of A, which is what I don't know. Everything else I know. Okay. Watch your signs here. I've seen some common mistakes, right? We set up our Newton's second law, and then we set up our, or then we solve for a variable, and maybe we miss like a negative sign, right? Or we subtract when we should add, or something like that. So just be careful, practice good algebra, and get good expressions. So I've got T1 and T2 both in terms of A. So before I substitute these in, I'm going to simplify this just a little bit. Okay, so I've got T1r minus T2r is 1/2 mr squared alpha. So I substitute A over R in for alpha right here, and one of those r's goes away. That's nice. Okay, one of those r's goes away. So now I have T1r minus T2r is 1/2 the mass of the disk, r times A. So this is good. I've got my three equations. I've got three variables, t1, t2, and a. But something else I notice in this step is that every term has an r in it. I know what r is, that's great, but it turns out that I won't have to use it. So that's nice. Every term has an r, so I can cancel an r out. So now I've got, this is my simplified version of my Newton's second law equation for the pulley. So it's t1 minus t2 is 1/2 the mass of the disk times the acceleration. Now this is ready for me to substitute these two expressions in for t1 and t2. So this is my expression for t1, it's going in right here. This is my expression for t2. It's got more than one term, so I'm going to be careful, be a good algebra person, and put my parentheses in there. This is my expression for t2, substitute it in there. Now I've got an equation, messy, it's got a lot of terms, right? So we got to be careful, but it's in terms of a, right? A is the only thing that I don't know. I've got the masses of everything, I've got g. So I'm ready to do my algebra and solve for a. Distribute the negative sign, right? So now I have negative m2g minus m2a. This term has an a in it, this term has an a in it, this term has an a in it. So I'm going to add this term and this term to both sides of the equation. Get all the terms with a in it on one side. So these are my three terms with a in it. I'm left with m1g minus m2g on the other side. We'll factor out an a. Okay, all three of these terms have an a. We factor that out. I'm left with this expression right here. Ooh, it's got all those masses in there. I'm ready to plug my numbers in. I'm not going to do it yet. Okay, I want to, but I'm not going to yet. I'm going to divide both sides by this whole thing right here. 1/2 m sub d plus m sub 1 plus m sub 2. Now I'm ready to plug everything in. I got a nice expression for the acceleration. Okay, nice expression for the acceleration. Substitute all my values, and I've got a linear acceleration for 1.5 meters per second squared. So I've got the acceleration. I do like doing the substitution method because I already have expressions for t1 and t2, and the majority of the time these are things that I got to solve for anyway. So I've already solved these two equations for t1 and t2. All I have to do is substitute a in for those expressions, substitute my acceleration in for those two expressions, and I can calculate t1 and t2. And here are my tensions. And again, you see they're not equal, which makes sense because the pulley has to be rotating, and it's rotating clockwise. Again, it makes sense. This is a reasonable answer because t1 is greater than t2. If I go back to my problem, or go back to my diagram, if t1 is greater than t2, then this object is going to rotate this way. So I feel good about my answers. I checked the situation, and it seems like it's reasonable, right? T1 is greater than T2, and it matches my coordinate system. I've got a clockwise angular acceleration for the pulley. Okay, so we're still doing Newton's second law. We're just tacking on a new object that has a mass and is a solid object and is rotating. So basically we're introducing a new equation, a new relationship between three objects, two of which are moving traditionally, right, translationally like we used to deal with, but one object we have to account for its rotation. So now I'm going to change the problem up a little bit, right? So I'm going to put this 5 kilogram mass, M2, and I'm going to put it on a horizontal surface. Okay, I'm going to put it on a horizontal surface. Again, this looks very familiar, right? This is kind of how I like to design the problems. All of our problems are going to look very similar to what we've dealt with in the past, but now we're adding these new properties that we neglected prior to Chapter 8. So I'm going to put M2 on a horizontal surface, right? And I do believe there is friction involved, right? There's a coefficient of friction between the surface and M2 of 0.25. So we're releasing the system from rest. We're looking for the speed of the system after the hanging block drops 2 meters. So this feels like a conservation of energy problem or a work energy problem that I dealt with back in chapter 5, right? Release from rest, what's the speed? I don't want to do Newton's second law and kinematics. I'd rather use energy concepts. So we're going to set it up very, very similarly to a chapter 5 problem that we've encountered before. So there's friction. I have to remember that there is work being done. So work is not equal to 0. So I'm going to have to use the dot product definition of work to calculate that work done, or at least get an expression initially. So it's equal to the change in energy of the system. So it's equal to the change in the kinetic plus the change in gravitational potential. No springs, so I don't have to worry about any gravitational potential. So I handle this the way I used to. Let's get rid of all those terms that I know are 0, so I'm not carrying them along with me. It says the system's released from rest, so the initial kinetic energy is 0. And again, I'm an amber, right? I like to be an amber. The lowest point of the 7 kilogram block is going to be the 0 potential position of that block. So the final potential of the system is 0. Again, like in our chapter 5 problems, I recognize that this block is moving horizontally. It's not going to travel in the y direction, so it doesn't change, or its potential energy doesn't change at all. So I don't have to account for the change of potential of this block, just my 7 kilogram block. Okay. So I can cross out my U final, cross out my K initial. So work is equal to K final minus U initial. I've got to find the speed of the block. Now, again, just like in chapter 5, the speed of this block is going to be equal to the speed of this block after they both travel a distance of 2 meters. So let's do what we did before and find an expression for the work due to friction. The frictional force is doing the work on M2 and it's traveling a distance d. What is the distance that M2 travels? It travels 2 meters, just like M1, right? They're still bound together by these two, or by this cable, right? Now in this case T1 and T2 are different, but I'm not being asked that, so I don't have to set this up just yet. So M2 is going to travel a distance d, M1 is going to travel a distance d, but that d is h, 2 meters. Okay. The frictional force is mu times the normal, and then the normal force is the gravitational force. Okay, it's the gravitational force on M2. Okay. So that should be a 2 right there. I did fix it later on. Okay, so I'll go in there and fix that quick, but I did catch myself right here. So this is mu times the gravitational force on M2 times the height, the distance it travels. It's the height that M1 descends. What's the angle between the frictional force vector and the displacement vector? It's 180. Cosine of 180 is -1. Again, the frictional force is doing negative work. Right, so it's taking energy out of the system. Energy is being taken out of the system in the form of friction. Okay, so I've got my work expression, negative mu M2GH is equal to K final minus U initial. Now U initial is M1GH, right? It's M1GH for M1. What's the final kinetic energy? M1 is going to have a kinetic energy, 1/2 mv final squared. M2 is going to have a kinetic energy, 1/2 m2v final squared, right? Both of these objects, M1 and M2, are going to be moving. So they're both going to have a translational kinetic energy, right? 1/2 mv squared for both. But the pulley, I cannot neglect its mass anymore, so it is going to have a 1/2 I omega squared, right? It's not rolling, right? It's not rolling down a hill, so it's just rotating, but it does have a final rotational kinetic energy. Okay, I know the rotational inertia of the disk, 1/2 mr squared, so I'm going to substitute that in, 1/2 the mass of the disk r squared. But again, I recognize that the problem is asking me for the speed. So I'm looking for V final. So I have to take this equation and I have to get rid of all the terms that I don't know by substituting something I do know or something I'm looking for in. And the only thing I don't know here, see, I know the coefficient, I know all the masses, I know the height, right? I know everything except for V and omega, right? So this is common, right? I'm going to have V and omega, both are unknown, but I can rewrite omega, my angular velocity, as the linear velocity divided by the radius of the disk. So I'm substituting the moment of inertia in here, but I'm also substituting V over R in for omega. So I can get rid of that omega and then solve this for V. Again, I got a lot of terms. It's really messy. I got to be careful, take my time, do my algebra very carefully here. So when I substitute these expressions in for I and omega, I see that the R squareds go away. R squareds go away. These fractions are going to combine, or they're going to combine. 1/2 times 1/2 is going to be 1/4. So now I've got a nice equation. Well, not nice, but you know, it's an equation that I can solve at least. I've got V final squared in 3 of these terms. Everything else I have values for, so I'm ready to solve for V final. So I'm going to add M2GH to both sides, right? M2GH, sorry, that's a 1. I got a couple mixing up my subscripts, so sorry about that. So this is M1GH, okay? So I'm going to add M1GH to both sides, right? So I'll get M1GH minus mu M2GH on one side, and then all my terms with V final squared are on the other side, okay? So I'm ready to factor out a V final squared. When I factor out my V final squared, I'm left with the 1/2 M1 plus 1/2 M2 plus 1/4 the mass of the disk. So I'm dividing both sides by this whole thing. Again, it's messy, but I know what that value is, right? I know all the masses, so I can just calculate it at the very end. Divide both sides by this entire expression, and then take the square root of both sides, and I've got a nice expression for V final. Again, not nice, but it's at least something that I can evaluate, right? I've got the numbers, so I can plug in my values. All the masses, the height, the coefficient of friction. So what I did was, in this step, I also factored out a GH from both sides just to make my calculation, or from both terms, just to make my calculation a little easier. So both of these have a GH. So I've got GH times M1 minus mu M2 divided by 1/2 M1, 7/2, 1/2 M2, 5/2, and 1/4 the mass of the disk, which is 1/2. And I get a final velocity of 4.2 meters per second. So I'll go back and I'll fix my little subscript issue here, just for clarification. But I'm probably getting a little long in this video, so I'm going to stop it, upload it, and then we will pick up with static equilibrium and angular momentum, and that will be the end of this course, right? That's great. So our 4th exam will be on all of chapter 8. Okay, so I'm going to stop this, and I will pick up with this slide next video, static equilibrium. Thanks.